Okay, today we're going to look at the ideal gas law. We have pressure times volume equals number of molecules, the Boltzmann constant, and temperature. What is the Boltzmann constant? Here you go. Boltzmann constant is a number, and it refers to the energy per molecule times Kelvin. You might have seen this before, and you're like, doesn't look like what my chem teacher told me. Can't believe both. Let me fix that for you. All right, in chemistry, we've got something like this. Instead of the Stefan-Boltzmann constant, you're going to have this baby R in joules per mole Kelvin. And then we have number of moles, so we have a little n here. Of course, you can relate K and R. They're each constants going from molecules to moles. How do you do that? Little quality Avogadro's number. All right, let's use this baby to blow up a balloon. I'm gonna blow up this balloon. Wow, that took more pressure because I have to expand the balloon against the atmosphere. But now the pressure is equilibrated. Pressure inside and pressure atmosphere are equal. Let's add some more volume. What's happening to your balloon? The whole point of blowing up a balloon is to increase the volume of air inside the balloon. Well, how do you do that? Do you boil it? No. The balloon expands because you're adding more molecules. Here we go. Let's look at the volume of this balloon. Now, it's not perfect, but let's take a radius measurement. Good. 62. Now let's take this baby and we'll put it in the freezer. But the balloon is sealed, okay? The sealed balloon then fixes the number of molecules. So number of molecules, constant. So what are some things that can change about our balloon? Some long time has gone by. Let's check our balloon. Frosty doesn't really look that much different upon first glance, but let's measure it. At the largest part on our balloon, it now only measures 56 centimeters. So what happened? So number of molecules, constant. Well, the pressure again will be generally atmospheric, so we expect a volume change. A dramatic temperature drop using liquid nitrogen. You can really see the volume in the balloon changing. But what if you had a more rigid container? So you drop the temperature, but volume can't change. Your car tire? What happens to it in the winter when the temperature goes down? Yep, you're right. The pressure goes down. Boop. Which then kind of leads to this flat bottom situation. Now, what is constant? The number of molecules is constant because you do not have a hole in your tire. And the volume of your tire is constant because it is in a tube that has a fixed volume. So the pressure will be seen to be dropping below the suggested tire pressure value. So what do? You fill her up.
Lose it. Step 5. Place the air hose fitting on the valve stem and press down. You'll hear the air inflating the tire. If you feel the air...
What does it mean to fill your tire up? It literally means that you're going to increase the number of molecules in that tire. So your tire is then going to look full again. So add N and bam, nice full tire. Pressure will be restored to the proper value. All right, here are two gas law equations and the constants that we're going to use. Please just think about when the appropriate situation is to use each one. So if you're given molecules versus if you're given number of moles, right? And you can convert between the two with Avogadro's number, or these two constants are listed on your formula sheet. So let's do a sample calculation real quick. So I'm going to choose to use this equation because we're talking about a single mole of air. So I'm going to use the NR version. And if we are at atmospheric pressure, okay, then we have volume unknown, we have a single mole of air, N is 1. R is always that same number, and our temperature is going to be room temperature, 293 degrees Kelvin. Remember, that comes from our chart that we talked about in the beginning. Solve for volume. Just to do a little division, take this, divide by your pressure. Bam. And our volume will come out to be 0.024 cubic meters. Just a warning, when converting cubic meters into centimeters or something like that, you have to convert 3 times. So if you want to convert this into cubic centimeters, you would need to multiply by 100 3 times, 1 for each dimension. All right, let's go ahead and look at example 2. We have 4 sealed containers holding different amounts of an ideal gas at different temperatures and pressures. Whew. The pressures in each is given, the number of molecules, N, and the volume. So watch out here. See, this is more an NkT situation. We'll rank the temperatures. Go ahead and give it a try. So we're going to write your temperature out. So use PV equals NkT. So if you solve for T here, you get P times V over Nk. So who's got the largest combination of P times V over N value? Okay, so on top of each container, we'll write out P times V over N. Now we can rank them. So A is greater than B, which is equal to C, which is greater than D. All right, next problem is having 2.34 grams of carbon dioxide. Ooh, let's convert that to moles. At STP, this is standard temperature and pressure. It's something that when you see STP, standard temperature and pressure, you have to feel comfortable just putting 273 Kelvin and 1 atmosphere in there. So let's convert first. 2.34 grams and 1 mole has 44 grams. So that's going to give us 0.053 grams. From there, we can plug into PV equals nRT. So you have your standard pressure. Make sure to pay attention to how many sig figs your problem wants you to use. Volume, the N we found above, the R, which is constant, and the temperature. Solve for the volume and get 1.19 times 10 to the negative third cubic meter. The last thing I want to point out is that finding pressure using area and a force is still something that we're going to do in this unit. It still applies here just as in fluids. Pressure is force over area. If you're ever given anything about a weight or a mass on top pushing, you should think about that equation, connecting it to PV equals nRT.